In this lesson, we explore the first decision tree splitting measure, which is the information gain. We are going to discuss entropy, information gain, and gain ratio. The most popular splitting measure in decision trees is information gain. To understand information gain, we need to discuss entropy, or what's called the Shannon entropy, at length. So entropy is a measure of uncertainty. And let's consider the canonical example of flipping a coin. So flipping a coin is a random variable, let's call it y, which has two distinct values, 0 or 1. Let's say 0 for tails and 1 for heads. If the probability of each outcome is 0.5, so this is the maximum uncertainty. It's hard to predict which outcome. Is it going to be a 0 or a 1? But let's say if the probability was 0.01, then this is more likely to be a 0. Or if the probability was 0.9, this is more likely to be 1. So entropy quantifies this uncertainty mathematically. The way entropy is defined as the probability of outcome 1 times log probability of outcome 1, outcome 2 log probability of outcome 2, and if you have m possible outcomes, then you basically sum over them. And this minus sign to make the term positive. And higher entropy means higher uncertainty, lower entropy is lower uncertainty. Let's try to understand information gain at high level without getting distracted by formulas and concrete numbers. Before splitting, we calculate the entropy for the entire dataset. In this example, there are two classes, green and red. We have 6 green and 6 red, which means this is a high entropy, maximum uncertainty. After the split, we compute the entropy of each resulting subpopulation. If a subpopulation contains only one class, as in none and in some, this is great because all instances belong to the same class. There is no uncertainty. But if a subpopulation contains a mix of classes, then the entropy will be something greater than 0 because there is some uncertainty. Now, to determine the overall entropy after the split, we calculate a weighted average of all entropies of all subpopulations, which means the none and the sum and the full. Now, information gain is the difference between the entropy of the data set before the split and the weighted average of all entropies of all subpopulations after the split. Large information gain is a great thing. It means entropy was high before the split, but low after the split. In other words, a large information gain indicates that the entropy high before the split and significantly lower after the split. And this is how we got the larger information gain. That was the high level overview. Now we will go through the definitions and concrete examples. Now we get to the details of computing the conditional entropy of the response variable y computed after partitioning the dataset on the attribute x. As we just explained, the conditional entropy quantifies uncertainty after the split. The conditional entropy of y given the attribute pattern is computed by taking a weighted sum of entropies of y for each possible value of pattern. And the weights expressed by p of x are the probabilities of each value of pattern occurring in the dataset. We are going to see a concrete example to get to the details. In this example, we want to compute the information gain for the attribute patterns, and we have 12 examples, 6 true, 6 false. To compute the entropy before the split, we are going to plug in the values. So -6, so we have 6 true example over 12 in total, log 2, 6 over 12, and again another 6 over 12 for the false. The entropy here is 1, which is a high number because there is a high uncertainty before the split. Next, we compute the conditional entropy for the values of the pattern, which are none, sum, and full. And as you can see, for the none and the sum, this is a clean split. So I have 2 false, and here I have 4 true, which means the entropy is going to be 0. For the full case, it's mixed. There should be high uncertainty here. We have 2 true and 4 false. So when we plug the numbers to the formula, we got 0.9183. This is a high entropy and there's a high uncertainty. In the last step, we compute the difference between the entropy before the split and the conditional entropy. Here we have 1 minus 6 over 12 multiplied by the entropy of full. And notice we don't have to deal with the zeros in the none and the sum case because anything multiplied by 0 is going to be 0. Next, we compute the information gain for splitting using the type attribute, the same entropy before splitting. Then we compute the conditional entropy for type. So for French and Italian, we got 1, and the same thing for Thai and burger, we also got 1 because it's the same ratio. 1 here and 1 here, then 2 here and 2 here. Now we compute the information gain, and in this case, we can see the weighted average and the conditional entropy. So 1 minus the weight of the French multiplied by the entropy of French, the weighted average for Italian, Thai, and burger. And here we end up with information gain of 0. So it's clear that information gain of 0.5 something is much better than 0. Here we summarize the previous 3 formulas used to compute the information gain using 2 notations. The notation using conditional probability and the notation using expectation. In other words, the expected information or entropy to classify a tuple in the dataset. Here, information needed to classify D after the split, and again, the same information gain formula. In the following slides, we will walk through computing the information gain for the play golf dataset, and we're going to try to split using Outlook and other attributes. And recall that there are 14 examples, 9 yes and 5 no. And to compute the entropy before the split, we plug in the values, minus 9 over 13 log 2 9 over 13, then minus 5 over 13 log 2 5 over 13. And we end up with 0.94. So this is the entropy before the split. In the next step, we compute the conditional entropy for splitting over the Outlook. And without loss of generality, we are using the expectation notation. For the sunny case, there are 2 yeses and 3 nos, and we plug in the values and get 0.971. Overcast is going to be 0 because it's a clean split. And again, rainy, 3 yeses and 2 nos, we are going to end up with the same value, 0.971. Now we compute the weighted sum for the conditional entropy, and we end up with 0.694. To compute the information gain, we are going to find the difference between the entropy before the split and after the split, and we get 0.246. To evaluate the remaining attributes, temperature, humidity, and windy, we apply the same steps and we end up with these information gain values. And as you can see, outlook is the attribute with the highest information gain among these options. It's wonderful that we covered the bases in information gain, and we still have one issue to discuss. The issue with information gain as a measure, it's biased towards those attributes which are going to give larger number of values. Think about date and ID. But from an information gain perspective, this looks ideal because each subset appears to be perfectly pure. However, this is misleading because now the data is being split into an excessive number of nearly empty groups. To overcome this issue, there is a refinement in information gain where we are going to compute something called the split info and divide the information gain by this split info. So the gain ratio is going to adjust information gain by considering the intrinsic value of the split. It's going to account for how evenly the data is divided among the attribute values. Let's see an example. Here is the formula for computing the gain ratio, information gain over split info. We already computed the gain for the temperature in a previous step. Now we compute the split info for temperature. We have hot, mild, and cool. We plug in the values and we get the value of 1.557. Then we compute the gain ratio for temperature, and for sure we have to do it for the other attributes and compare and compute the one with the best gain ratio. In summary, in this lesson, we explored the first decision tree splitting measure, which is the information gain. We discussed the entropy and the gain ratio.